This is the Semester 1 final exam review. I'm going to talk about problems 25 to 34 on the review packet. So in problem 25, they ask you to simplify if possible. To start, determine if the expressions contain like radicals. When adding and subtracting expressions with radicals, the radicals are kind of like terms. You know, like if you add 2x plus 3x, you get 5x. But if I ask you to do 2x plus 3y, you can't add them because they're not like terms. Or 2x squared plus 3x. They might both have x's, but they don't have x's to the same power. So we can't combine them. As long as the radicals have the same root index and the same number or letter or combination of numbers and letters under the radical, they can be added. So 3 the square root of 5 plus 4 the square root of 5 is just 7 the square root of 5. Notice that you don't actually add the 5's under the radicals. They work like your x's. In B, 8 the cube root of 4 minus 6 the cube root of 4, well, they have a like term, and 8 minus 6 is 2. Notice in C, however, we have the square root of xy in the first term and the square root of y in the second term. I cannot combine them, so we say it's already simplified. D, 9 the square root of 3 plus 2 the square root of 3 is 11 the square root of 3. All right, 5 the square root of 2 plus 2 the square root of 3. These are not the same, therefore they cannot be combined, so we just say it is simplified. F, watch out. Make sure that they have the same radicals, because if they don't, you can't combine them. Since the square root of 7 is not the same as the cube root of x, it is simplified. All right. G, 14 the cube root of xy minus 3 the cube root of xy. They have the same radicals, so it's 11 the cube root of xy. And H, 8 the cube root of x plus 2 the cube root of y, they're not the same, so it's simplified. For problem 26, just ignore this. This was a problem with where I got my picture from. It says a floor tile is made up of smaller squares. Each square measures 3 inches on each side. Find the perimeter of the floor tile. Well, you know perimeter means add all the sides. So these squares are each 3 units apiece, or 3 inches, I guess they told us. But here's the problem. This is not a side of the square. That's actually the diagonal. So if that's the diagonal and the 2 sides of the square meet up at a right angle, because we know that the angles in a square are 90 degrees, how would I find the length of that diagonal? Because all of these pieces are diagonal. As a matter of fact, there are 8 of them. So if I could find the length of one diagonal, I could just multiply that answer by 8. Well, if it's a right triangle, we have this fun thing called the Pythagorean theorem. You know, a squared plus b squared equals c squared. I don't like that formula because I think sometimes students forget that c is the hypotenuse, but this is the hypotenuse of the triangle. So 3 squared plus 3 squared is equal to c squared. That's 9 plus 9. 18 is equal to c squared, so c must be the square root of 18. But here's the problem. I have to simplify that radical. How do you simplify it? Well, you either know that this is 9 times 2, and the square root of 9 is 3, or you can rewrite 18 using prime factorization, you know, the factor tree. And you would find out it's 2 times 3 times 3, and a square root means pairs, and there are a pair of 3's. Either way you do it, you find out that the side length is 3 to the square root of 2. So if there are 8 pieces, 1, 2, 3, 4, 5, 6, 7, 8, all which have 3 to the square root of 2 as their length, all you have to do is multiply this by, 8. I got to multiply by the right number. And you get 24 to the square root of 2 inches as the perimeter. Problem 27 says, what happens at the x-intercepts of f of x is equal to x minus a, x minus b squared, x minus c cubed? What is the degree of the function? Well, remember what happens at the multiplicities. So one of the x-intercepts is x equals a. But it has a multiplicity of 1, which means that if I were to graph it, wherever a is, let's say a is here, the graph would just pass right through it, like a line. Another root is at b, but b has a multiplicity of 2, which means if I call this b, that means the graph has like a quadratic shape at that x-intercept. And the other solution is that x equals c, but it has a multiplicity of 3, which means that it has, it has a cubic shape at that root. And I probably didn't do a very good job of drawing this picture, but I wanted to give you sort of just a basis for what it looks like. I think my picture is actually upside down, because the last question is, what's the degree of the polynomial? You don't have to multiply it completely out to determine the degree. The easiest way to do it is you will have x to the first from the first parentheses. This will be x to the second, and this will be x to the third. That means there are 6 x's. And the graph actually probably should look like this, because the first term would have been positive x to the 6th, in which case it would have opened up rather than down. Let's do something similar to the last problem. In number 28, we want to determine the zeros of f of x is equal to x, x plus d, x minus e squared. And then we want to determine what the degree is. Well, the zeros are x equals 0, x is negative d, and x is e. Remember, you're going to find out the degree by multiplying x times x squared. That gives us 4 x's, which means it's a 4th degree polynomial. Although we haven't reviewed properties of exponents, we did do this in Algebra 1, so hopefully this will spark your memory. I want to simplify this expression. Here's the first thing. Since the outside exponent is to the negative 4th power, we don't like negative exponents. Anything to the negative exponent just means to flip the fraction. Our definition from Algebra 1 was that, I should write this as x to the negative nth power is the same as 1 over x to the nth. So I'm going to start by flipping this. When I flip the fraction, it changes that exponent to be a positive 4. Next, another property of exponents says that if you have an exponent on the outside of parentheses, you distribute it to everything inside the parentheses. And it doesn't matter if it's over division or over multiplication, or both occurring at the same time. So I'm actually going to raise, I'll use a different color, I'm going to raise this, this, and this all to the 4th power. Well, when I do that, how does that work? Well, we have another property of exponents that says something to a power, you just multiply the exponents. So in order to do z to the 1/2 to the 4th, I'm going to do 1/2 times 4, which is 2. Then in the denominator, x to the 3/4 to the 4th is just 3/4 times 4, which is 3. And then y to the 4th. And there, it's simplified. Problem number 30 asks you to rewrite the zth root of x to the y power with fractional exponents. What does each variable represent? All right, so there is a property of radicals that says that you can rewrite a radical by taking the root index and making it the denominator of a rational exponent. So this becomes x raised to the y over z power. X is called the base of the exponent. Y is it's the exponent. But z became part of the exponent, but z was really the root index of the radical. Given f of x is equal to 3x squared plus 6x minus 1, determine the following. Let's start with the axis of symmetry. Remember, you can find the axis of symmetry using the formula negative b over 2a. Negative b is 6 over 2, a is 3. So we get negative 6 over 6, which is negative 1. What does the axis of symmetry represent? It is the x-coordinate of the vertex. So you actually know half the vertex. Well, how do you find the rest of the vertex? You plug the axis of symmetry back in to the equation for x. So we're going to do 3 times negative 1 squared plus 6 times negative 1 minus 1. Oops. Which is going to be 3 minus 6 minus 1, which is negative 3 minus 1, which is negative 4, although you're just going to plug it in your calculator and get the right answer. So I shouldn't have boxed that because the vertex is at negative 1 comma negative 4. Number 32 was mistyped because it says write an equation of and graph a quartic polynomial whose solutions are negative 2, 4i, and negative 4i. Well, they only gave you 3 solutions. So that means this is not quartic, it's cubic. They would have had to have given you a 4th degree polynomial, or a 4th root, in order to determine that it was a 4th degree polynomial. I can tell you, however, that if this is 3 of the roots, the 4th root would be a real number and not imaginary. All right, so if these are my 3 roots, my factored form is going to be x plus 2, x minus 4i, and x plus 4i. I would recommend multiplying these two together first because it's the product of a sum and difference. That means when I multiply it together, the middle terms are going to cancel. So I'm going to get x squared minus 4xi plus 4xi. Oops, I did that backwards. The first one was plus and the second one was minus. And then minus 16i squared. All right, so those are opposites and they cancel. By definition, I squared is negative 1. But if you forget that, as long as you plug it in your calculator, the calculator will spit it out. So you get x squared minus 16 times negative 1, which is x squared plus 16. But I have not done anything with that x plus 2 yet. So now it's time to deal with that. So I'm going to FOIL again. X cubed plus 16x plus 2x squared plus 32. And that would be the cubic polynomial whose solutions are at negative 2, positive 4i, and negative 4i. Now, what would the graph look like? Well, just as a general sketch, because the graph only has one real solution at negative 2 and the other 2 solutions are imaginary, and because it starts with a positive x cubed, the graph would look something, try that again. Like this. It would only touch the x-axis at one location, but it would still go up from left to right. Problem 33 says let f of x equal x cubed minus 9x squared plus 15x plus 25. Determine all the solutions for the function, write in standard form, and graph. I think the person who wrote these notes made another mistake because the original equation is already in standard form. So what we're going to do is we're going to find the solutions and write it in factored form. One of the nice things about the graphing calculator is that if you're feeling like doing factoring is it's difficult, it's a difficult process, one of the factoring cheats you can use is you can graph it on the calculator, find the zeros, and work backwards. So this third degree polynomial hits the x-axis 2 times. It hits at x equals -1 and x equals 5. But I want you to notice the shape of the graph at 5. It's a multiplicity 2. That means it actually has 2 solutions there. So the factored form would be x plus 1 and x minus 5 squared. Given a quadratic function, it is possible to have 2 real solutions, one real solution, one real repeated solution, or 2 complex solutions. List the possible solutions for cubic, quartic, and the last one should say quintic. Now, in order to do this, I'm going to go backwards. I'm going to erase this because I'm going to go back and I'm going to show you what we learned when we did quadratic equations. Those were the ones whose biggest exponent was 2. There were 3 things that could happen. You could either have 2 real solutions, that's our 2 real. This we called 1 real, except it's a repeated root because it's not really 1 solution, it's actually 2, they're just the same. But the third thing that could happen is the graph could never hit the x-axis at all, in which we learned that it was actually 2 complex solutions, the ones with imaginary numbers. So now let's talk about a cubic function, which looks like this. So if I draw a cubic function, could I draw a cubic function that hits 3 times? Absolutely I can. Remember that cubic functions, x cubed, the most amount of times it can hit the x-axis is 3. So I could have 3 real solutions. Could I draw this so that it only hits twice? Well, I could do this. Look, it only hit twice. But that one is one of those multiplicity 2. So again, it has 3 real solutions. All right, so what happens if I draw it so it only hits once? So it has 1 real solution. Well, then what must be true about the other 2? The other 2 must be complex. There is no way to draw this polynomial so that it hits 0 times. Because one end of the graph goes up and the other end goes down, it is always going to hit the x-axis at least 1 time. All right, let's go to the next one. Quartic means x to the 4th, and we said those graphs looks like m's and w's, but they could look like parabolas. So let's start with this. 1, 2, 3, 4 is the most amount of times that it can hit the x-axis. So it could have 4 real solutions. I can also draw it so that it hits 3 times. Watch that. 1, 2, 3. Except because this one over here is a multiplicity 2, it still has 4 real roots. Now let me go and show you what happens if it only hits twice. And I'm going to keep using the M shape just because I like that one. What if I do that? It only hits the x-axis twice. But look, they're both multiplicity 2, so it's still 4 real solutions. How about if I go and I draw it a different way where it hits twice? Watch this. Remember, the M and W, they're not necessarily symmetric, so it could be kind of warped. look at this. It hits twice, but they're not multiplicity 2's. So if 2 of them are real, then 2 of them are complex. Oops. All right, now I'm going to go draw it another way. What if this only hits the x-axis one time? Remember, even though it hits one time, that is a multiplicity of 2, so it's still 2 real roots and 2 complex roots. Is it possible to draw a quartic function so it never hits the x-axis? Absolutely. Anytime you have a polynomial that is even powered, 2, 4, 6, 8, both ends either go up or both ends go down. So because the degree is 4, this would have 4 complex roots. Now let's talk about quintic. So it should say Q-U-I-N-T-I-C. Quintic are 5th degree polynomials. A 5th degree polynomial can hit the axis at most 5 times. 1, 2, 3, 4, 5. So it could have 5 real roots. What happens if I only make it hit 4 times? So 1, 2, 3, 4. Well, if I only hit 4 times, I want you to notice that one of them's a multiplicity 2, so it still have 5 real roots. Now let's go see if I can draw it so it only hits 3 times. 1, 2, 3. Oh, if I go and draw this so it only hits 3 times, now it's got 3 real and 2 complex. Please remember that we talked about complex roots always come in pairs. You can never have one complex solution to a polynomial. You can only have 2, 4, 6, 8, and so on. All right, that was 3 times. I wonder if I can draw this so it hits twice. Hey, look at that. I drew it so it hits twice, except when it hits twice, doesn't it really still have 3 real roots because this one here is a multiplicity 2? Now let's see if I can draw it so it only hits once. There we go. Well, if it hits once, then it would have 4 complex roots. And the number of roots always need to add up to the biggest exponent. So it can have one real 4 complex, 3 real 2 complex, or 5 real. When we did quartic, it can have 4 real, it can have 2 real and 2 complex, or it could have 4 complex. When we talked about cubic, it could have 1 real 2 complex, or it can have 3 real. And those were your only options. And that is the end of the semester review packet.